Okay, so we've gone over graphing quadratics. Today we're going to go over graphing exponentials and determining whether or not a function is an exponential before even getting to the graph, just from our table of values. So first, we'll talk about what's called a common ratio. So the common ratio is calculated by dividing successive, that means one after the other, successive values. Common ratio will be consistent, that means the same, consistent throughout exponentials. So the common ratio, I'll show you what I mean by that right here. Let's look at example 1a. Common ratio, we are calculating it by dividing successive values. So that means ratio right here. And let's just extend this table like so. So our common ratio, just like first differences when we worked with our quadratic functions, here we're going to calculate it for each value except for the first one. So we'll cross off this first one here, and what we can do is we can take our 6, which is from when x equals 1, and our 3, which is from when x equals 0. We can divide them. So 6 divided by 3 equals 2. Perfect. And then let's just write that a little bit neater here. 6 divided by 3 equals 2. And then I can do that same thing for the next one. Here I'm taking the 12, dividing it by 6. So 12 divided by 6 equals 2. Perfect. 24 divided by 12. Oops. 24 divided by 12 equals 2. And we do notice our pattern. 48 divided by 24 this time. 48 divided by 24 equals 2. So when our ratios are consistent, that means that we have an exponential function. So here, what the question is asking us is determine if the following table of values represents an exponential function. Since values are common, since the ratios are common, therefore this is an exponential. And we can try that same strategy for example B. Our ratio, we don't calculate anything for the first one, and then we do 10 divided by 5. Well, 10 divided by 5 equals 2. And then we do 15 divided by 10. Well, 15 divided by 10 doesn't equal 2. That equals 1.5. We'll try the next one just to make sure we didn't make a mistake there. 20 divided by 15. 20 divided by 15. 20 divided by 15 is 1.33. We notice our numbers are getting smaller. The big thing that we notice is these numbers are not the same. So since ratios are not common, therefore this is not an exponential. Now we could have noticed anyways, just from looking at the values within this table, we may have recognized that that one's a linear function. But here we're going to jump into example C. Again, we're going to calculate our, we're going to calculate our common ratios here. Ratios, don't calculate the first one. And then I do 60 divided by 120. We always do the second one divided by the first. So 60 divided by 120, that equals 0.5. And then I can look at my, just going to clean that up here, equals 0.5. Looking at the next one, 30 divided by 60. Well, if I put that into my calculator, it equals 0.5 again, so that's a good start. We'll try it once more. 15 divided by 30 equals 0.5. I see where this is going. 7.5 divided by 15 equals 0.5. So since the ratios are common, therefore this is an exponential. So you should be able to do D here on your own. I'll leave that for you. And we'll work on example 2 now. Here what we're doing is we're going to graph. So we'll create a table of values first, and we'll just graph the points. So if we take our calculator out, so if I put 2 to the power of -2 into my calculator, that's 2 to the power of -2 into my calculator, I get 0.25. Now I'll try 2 to the power of -1 into my calculator, and I get 0.5. Okay, now I'm putting 2 to the power of 0. Well, I know anything to the power of 0 is just 1. And 2 to the power of 1, that's just itself. 2 to the power of 2 is 4. And 2 to the power of 3 is 8. If I wanted to, I could check my ratios here. Not going to right now, but because this is an exponential, which we see from the form of our equation here, then our ratios would be common. And let's see here. So if I'm graphing it, I'm going from the first one, which is from -2. I have 0.25. And then when x equals -1, I have 0.5. When x equals 0, I have 0. X equals 1, I have 2. I can see that it's increasing at a faster rate here as I look from left to right. And when x equals 2, when x equals 2, then y equals 4. When x equals 3, y equals 8. And if I wanted to do one more, when x equals 4, it would come all the way to 16. That would just be the last one that would even fit on here. So my curve here would look something like this. And we'll try here. Now, as an aside, if we calculated our common ratios for this question here, I would do 0.5 divided by 0.25, which is 2. I would do 1 divided by 0.5, which is 2. 2 divided by 1, which is 2. And I notice here that all of my common ratios, they're the same number as my base that's right here. That's just an interesting thing I noticed when I worked through that problem. We'll do one more example. We'll do one more example here, this one with a base of 1/4. That's 1 divided by 4. So when we're putting this into our calculator, we'll need to either make sure that we keep these brackets there, or we handle it in some way that lets us make sure we're calculating accurately here. So if I have 1/4 to the power of -2, well, that's going to be 16. If I do 1 over 4 to the power of negative 1, that's 4. If I do 1 over 4, that should have been in brackets, 1 over 4 to the power of 0. Well, anything to the power of 0 is just 1. And then I can do 1 over 4 to the power of 1 is 1 over 4, that's 0.25. And 1 over 4 to the power of 2, which is 0.0625. 0.0625. I know that I'm getting very small very quickly here. And 1 over 4 to the power of 3 is 0.016. So I can plot these points. When x equals negative 2, then I see y equals 16. X equals negative 2, y equals 16. When x equals negative 1, y equals 4. When x equals 0, y equals 1. I'm getting smaller and smaller. When x equals 1, y equals 0.25. And eventually it gets so close, but it won't actually ever touch our x-axis there. We can draw this curve in like so. We'll note the shapes of these curves. This curve here on the left, it increases as we go from negative to positive x, right? This curve on the right, it will decrease as we go from negative to positive x. The reason for that, as you will find out, the reason for that is that the base of our exponential function in example A is 2. 2 is greater than 1, that means it's going to be shaped like this. If the base of our exponential function is 1 over 4, 1 over 4 is less than 1, that means the shape is going to be more like this. As a bit of extra homework, just kind of think about, reflect a little bit on it. What do you think it would look like if our base was 1 for an exponential function? So if our exponential function was y equals 1 to the power of x, just think about how you think that would look. So for homework, you should be able to work through all of the questions on the following page. The answers are at the bottom.